Okay, we're going to talk about bits and bytes. This is a little bit more advanced, not strictly necessary, but can be very helpful to know this. Um, so first of all, what's a bit? Bit can represent two values, 0 or 1. That's it. That's what computers work on, zeros and ones. There are 4 bits in a nibble, and there are 8 bits in a byte. So here's what a byte looks like when it's all zeros. 0, 0, 0, 0, that's one nibble. 0, 0, 0, 0, that's the second nibble. Together they make up one byte. So when you talk about a hard disk size or a computer having a gigabyte, that's a billion bytes of memory, or 256 megabytes, 256 million. That's what it means of those. And since each bit can be 1 or 0, there are 256 combinations, including all 0 and all 1. And so that's convenient. The ASCII system is a way of representing characters. So with 256 in English, it works really, really well. In other languages, not so well. So we have other ways of encoding other languages that use more bytes. We're not going to talk about that. What we are going to talk about is what some of the combinations of bits are. So on the left is binary, 0, 0, 0, 0, 0, 0, 1. So we're just looking at one byte, okay, and its value in decimal is 1. So if we move it over one place, this is 2. If we basically add these two together, this is 3. So there's the 2's place. We'll get to this in a second, the powers place. So this is 3, 4, so 5. So you can see how we're kind of just turning each bit on in sequence. 3. Once we get to all 3, we need to go up. Just like when you go from 0 to 9, you start back at 0 and you put a 1 here. The same thing happens in binary. You have a 1, so you turn this one to 0, you put a 1 here. Then you turn this one to 1. When they're both 1, the next one is a 1 here and zeros. So that's what we represent here. So this will become a little clearer. So this one is 1 times 2 to the 0. So this is the 2 to the 0 place. Anything raised to the 0 power is 1. So 1 times 2 to the 0 is 1. 2 to the 1 is 2. So 1 times 2 to the 1 is 2. Okay, so you can see this is the 2 squared. This is the position for 2 cubed. 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. Okay, so this is anything to the 0 is 1. This is 2, 4, 8, 16, 32, 64, and 128. So that's what these numbers are in decimal, and this is their representation in binary. And you can feel free to pause or watch this multiple times. So algebraic positional notation, that's what this is called. We use it in all our math. You may not know its name. So in binary, each position that we just showed represents an increasing power of 2. In base 10, which you're used to counting in, each position represents an increasing power of 10. So the number 123 is really 1 times 10 squared. That's that place right there. 2 times 10 to the first. That's that place. And 3 times 10 to the 0. Again, any number raised to the 0 is 1. So this is 100, 10 squared. 2 times 10 is 20. And 3 times 1 is 3. So 123. So this is really nothing new, but it might be a different way for you to think about it. So we talked about binary, where this is 2 raised to the power each position, 2 to the 0, 2 to the first, 2 squared, 2 cubed. So in hexadecimal, instead of 10, this is 16. So 123 in base 16 is 1 times 16 squared, plus 2 times 16, plus 3 times 16 to the 0, or 3 times 1. And in decimal, that would be 291. So 123 in hex is 291 in base 10. So now you have a little bit of an issue in it. You want to be able to represent 0 through 15 different things with your numbers. We have 0 through 9 in decimal. Those are our digits. But now we've got, in effect, 15 digits. So what we did was we just decided we were going to use letters. So A represents 10, B represents 11, C represents 12, D 13, E 14, F 15. All right, so that 1 0 in base 16 is the same as 16 in base 10. So my point here is you don't really have a digit 10. You have 0 through 9, and then 10 in decimal is really 1 times 10 to the first, right? Just so In base 16, you have 15 representations, and then when you want 16, it's 1 times 16 to the first. Okay. So 4 bits is a nibble, and that's nice in hex because 1 nibble lets you represent 0 through F. Okay, so 0, we kind of looked at most of these. 1, 0, 0 was 0 was 8, 1, 0, 0, 1 is 9. And then there's 10, 11, or A, B, C, D, E, and F. So let's think about the range, right? We talked about this. There's 8 bits. It's 1 byte. This is in hex FF. So in base 16, we would represent this in hexadecimal as FF. In decimal, this is 255. So with the value of all zeros, we have 256 different representations altogether, which is the same as 2 to the 8th, because there are 8 bits, so 2 to the 8th is how many different numbers we can represent. Okay. So with 2 bytes, that's typically called a short. In C++, you can represent a number as large as FFFF. Okay, each one of these is 4. 2 is 8, so this is 16. 2 to the 16th. If you get your calculator out, you'll see that's 65,536. So 0000 through FFFF is 65,536 different values. So when with an int, and they saw on most everybody's machine, this was 32 bits or 4 bytes. 2 to the 32nd power is 4 billion. And on a long int is 8 bytes. 2 to the 64th is 1.8 times 10 to the 19th, or 18 quintillion. So you can represent really large integer values with a long. And with a regular 32-bit int, you can represent 4 billion. And we briefly talked about whether those numbers are signed or unsigned. So it's 4 billion unsigned, 0 through whatever, and basically cut it in half if you're going to have half the numbers be negative. Okay. So base 8's not used much anymore, at least not by me, but it's the same thing. 123 is 1 times 8 squared, 2 times 8 to the first, 3 times 8 to the 0, and those are all the major bases for computers. And of course, any number, 2, 3, 4, 5, 6, and up beyond 16 can be a base, but these are the common ones, 2 and base 16, and of course decimal are the ones you'll be using when programming computers.